Hi, my name is Kimoni Nanya, and this is my rope physics lab. So in this lab, we analyze the spring mass system and captured its motion data. This motion is based on Newton's second law and the energy principle. Newton's second law states that velocity, which is the motion of a system, depends on the forces acting on the system and it's proportional to the mass. In this lab, the two forces acting on the system were the spring force and the force of gravity. These factors then play a role on the total energy of the system, and the energy principle states that energy is neither created nor destroyed, meaning the change in energy, which is delta E, should stay at a constant zero. The purpose of this lab is to examine the motion of a spring mass system and compare it to the computational model, then use this data to calculate the change in energy. My results showed that the observed versus computational were similar, but my observed model had longer peaks and my change in total energy was at a constant zero. So in this lab, we used a bunch of different models, and you can see the different formulas on the right, but to summarize it, we use Newton's second law, the spring force, the force of gravity, and the energy principle model. So the basis of this experiment is to use tracker to track the position of a mass that is attached to a spring. I calibrated it and measured it at 1.7 meters, and I noticed that I will likely have source of error in my experiment from this portion because by tracking you will have to track each frame and it needs to be centered, and I'm not perfect with that. And those are my initial conditions. My initial position is stated there, and my initial velocity is 0 because the object was at rest. So this lab had a lot of coding, so I'm just gonna give a brief explanation. On the top right, as you can see, I added my initial conditions, which was the mass of the ball, which was 0.402 grams, the initial position, and the initial velocity, which, as I stated earlier, the spring constant, I calculated that using the spring force formula, and I went ahead and calculated the L and L naught using the position formula because L naught is the relaxed length, so L is the current position minus the spring position, and L hat, that's the direction. It is the force, which is L divided by the magnitude, and S, that is once again the spring force, which is the magnitude minus L naught. And of course, if you look at the bottom, I went ahead and used Newton's second law, which is the F net, which is the spring plus the gravity added together, and that F net, use it in the velocity update formula, and then use that velocity in the position update formula. Then for the energies, as you can see, I went ahead and added the formula for potential and kinetic energy, and the total energy is all of those added up together. So for my position graph discussion, my observed data and experimental were similar. There isn't major variation, however, the computational model for both x and y component for some reason had shorter peaks, meaning the spring was calculated less stretched. My model also ended with higher predictions of the x and y components. So I'm thinking my experiment saw the string as more stretched versus the computational model. So to discuss my energy graphs, first I want to say delta E was at a constant 0, which proved the energy principle correct. And the change in spring and gravity potential energies had the same magnitudes, but they were in opposite directions because they were working against each other. And finally, the change in kinetic energy had a constant magnitude at the peak of each time oscillation. In conclusion, the energy principle was proven correctly. What does this mean? There was no energy added to the system, as its gravitational and spring energy worked against one another. The total energy on the system came from its kinetic energy, which stayed constant, meaning the total change in energy was 0. The period of oscillation for the y component was 1.519, while the x component was 1.71. I believe the y component is shorter because the way I chose my axis, the ball had a shorter distance to travel in the y direction than the x direction based on the spring.